Namaste, welcome to the lecture on linear algebra through geometry. In the last lecture, we looked at the idea of Gaussian elimination technique for solving system of linear equations. We looked at the idea of elementary row operations to obtain the row echelon form and the reduced row echelon form of a matrix. We also looked at the idea of pivot variables, free variables and rank of a matrix, etc. Further, Professor Arul Alan gave insight about how elementary row operations preserve the solution space. In this lecture, we will look at the idea of determinants, matrix inverse and Cramer's rule. Given a square matrix A, we associate the matrix A with a function called determinant function that associates a real number with a matrix A. Let A is equal to A11, A12, A21, A22. We define the determinant of A as determinant A is equal to A11 into A22 minus A12 into A21. Let us take an example 3 by 3 matrix A given by A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. Determinant A is given by determinant A or is equal to A11 into determinant of A22, A23, A32, A33 minus A12 into determinant A21, A23, A31, A33 plus A1 into determinant A21, A22, A31, A32. In the later modules, we will see that the determinant of A 2 by 2 matrix corresponds to the area of parallelogram determined by the 2 column vectors A11, A21 and A12, A22. Three by 3 matrix corresponds to the volume of a parallelopiped determined by 3 column vectors A11, A21, A31, A12, A22, A32 and A13, A23, A33. Computation of determinant of larger size matrices is cumbersome. Some comments. Determinant of A n by n where A is a diagonal matrix is equal to the product of diagonal elements If U is an upper triangular matrix, then determinant of U is equal to product of diagonal elements. If A is a square matrix of size n by n, then determinant of CA is equal to C to the power of n determinant of A for any scalar C. If determinant of A is 0, we say the matrix A is singular, else the matrix is non-singular. For n by n matrix A, if determinant of A is not equal to 0, then we say rank of A is n. For a square matrix A of size n by n singular, the following statements are all equivalent. A is a singular. The rank of A is less than n. Determinant of A is 0. A is not row equivalent to I n by n. Ax is equal to 0 has non-trivial solution. Ax is equal to b does not have a unique solution. That means no solutions or infinitely many solutions case. Now let us go to non-singular matrix. For a non-singular matrix A n by n, the following are equivalent. A is non-singular. Rank A is equal to n. Determinant of A is not equal to 0. A is row equivalent to 1n in identity matrix. Ax is equal to 0 has only trivial solution. Ax is equal to b as a unique solution X for every given B. Note that determinant of identity matrix n by n is 1. If two rows of matrix are equal, then the determinant of the matrix is 0. Determinant of A transpose is equal to determinant of A determinant of the product of two matrices is equal. Determinant of the product of two matrices is equal to the product of the determinants. That is, determinant of product AB is equal to determinant of A into determinant of B. Consider the following elementary row operations of swapping two rows. For example, if A is A11, A12, A21, A22. So, the determinant of A will be A11 into A22 minus A21 into A12. Suppose we swap R2 R1, we get the new matrix A RS is equal to A21 A22 A11 A12. The determinant of A RS row swapped is equal to A21 into A12 minus A11 into A22, that is minus of A11 into A22 minus A21 into A12, that is minus determinant of A. Thus, we see that elementary operation of row swapping changes the sign of the determinant. Suppose we will take some examples. A is equal to 1, 2, 3, 7. So, the determinant A is equal to 1 into 7 minus 2 into 3, that is 7 minus 6 is equal to 1. Another matrix A, B, 2, 3, 4, 8. So, determinant of B is equal to 2 into 8, 16 minus 3 into 4 minus 12. So, it becomes 4. Now, we will add the determinants A and B. When you add determinant A and B, we get 3, 5, 7, 15. So, determinant of A plus B 45 minus 35, that is equal to 10. Determinant of A plus B is equal to 10. Determinant of A plus determinant of B is 1 plus 4, that is equal to 5. Hence, the determinant of sum of A B is not equal to determinant of A plus determinant of B. However, suppose we take another matrix C 1 0 0 1. So, its determinant of C is 1. Another matrix D 0 1 1 0. So, the determinant of D is minus 1. Now, we add the determinants matrix C plus D, then we get 1 0 0 1 plus 0 1 1 0, that will be 1 1 and 1 1. Now, the determinant of C plus D is equal to 1 minus 1, that is equal to 0. Determinant of C is 1, determinant of D is minus 1, but determinant of C plus D equal to determinant of C plus determinant of D. Determinant of sum of matrices need not be equal to sum of determinants. Now, we will look at matrix inverse. What is matrix inverse? Recall that if A is a non-zero real number, we can find a real number A inverse such that A into A inverse is equal to A inverse into A, that is equal to 1. A inverse is called as the multiplicative inverse of A. This is A inverse, this A inverse is unique for a given real number A. Along the similar lines, we will try to develop the idea of inverse of a matrix A. Let us consider the following matrix A: A11, A12, A21, A22. We now ask the question, is it possible to find matrix B such that the product matrix A and B is equal to I, identity matrix? That is, AB is equal to I. We put a question mark because we still do not know if it can happen. So, let us multiply A11 matrix A and B and see whether it is equal to identity matrix. A11, A12, A21, A22 into B11, B12, B21, B22. Is it identity matrix 1 0 0 1? Let us find out the product AB. If you multiply these two 2 by 2 matrices, we get A11 B1 1 plus A12 into B21, A11 into B12 plus A12 B22. Second row, A21 into B11, A22 into B21, A21 into B12 plus A22 into B22. We equate this to identity matrix 2 by 2, then the following equations happen. A11 B12 will be equal to A12 B22 and and B21 11 is equal to minus from this we derive B12 is equal to minus A12 into B22 by A11. Similarly, B21 is equal to minus A21 into B11 by A22. Substituting for B12 and B21 in the equations with RHS equal to 1, we get A11 into B11 minus A12 into A21 into B11 by A22, that is equal to 1. So, the B11 is equal to A22 by A11 into A22 minus A12 into A21. Similarly, B22 will be A11 by A11 into A22 minus A12 into A21. B12 will be equal to minus A12 divided by A11 into A22 minus A12 into A21, and B21 is equal to minus A21 by A11 into A22 minus A12 A21. If we carefully observe the denominator in all the 4 values of B, the denominator turns out to be the determinant of A. Hence we can write B is equal to 1 divided by determinant of A, the matrix A22 minus A12 minus A21 A11. If the determinant A is 0, then the matrix, if the determinant is not 0, then the matrix B exists. The matrix B is called the inverse of A. B is denoted as A inverse. Also note that B into A is identity vector I. The matrix B exists if and only if determinant A is not equal to 0. What this means is the following. In order for a square matrix to have an inverse, its determinant must be a non-zero. Matrix must be non-singular. This implies that for a rectangular matrix, wide or tall, matrix determinant is not defined, meaning matrix inverse is also not defined. You will see in the next lecture by Professor Arul Alan the importance of inverse of a matrix. Let us now go ahead with properties of inverses. Properties of inverses. For any two invertible matrices A and B, of the same size, the inverse of the product is equal to the product of inverses in the reverse order. Let us prove it. Let A B is equal to C. Therefore, the inverse of product A B is equal to inverse of C. We know that C into C inverse is equal to I. That means, if you substitute C as A B and C inverse as B inverse into A inverse, finally it ends up in identity matrix I. That is, A inverse into A is I, B inverse into B is I. So, I into I is I. So, the moral of this story is the product of any number of invertible matrices is invertible. The inverse of the product is the product of inverses in the reverse order. If A is invertible, then A inverse is also invertible. That is, inverse of A inverse is A. If C is a real scalar which is not equal to 0, then CA is invertible if A is a invertible matrix. And inverse of CA is equal to C inverse into A inverse. If A is invertible, then A transpose is invertible, and inverse of A transpose is equal to transpose of A inverse. We have looked at the properties of inverse, but we are yet to formally define matrix inverse. Given n by n matrix A, the inverse is defined by A inverse is equal to adjoint of A divided by determinant of A. For 2 by 2 invertible matrix A, that is A11, A12, A21, A22, adjoint of A is equal to A22 minus A12 minus A21 A11. That is, swap the diagonal elements of A, change the signs of off diagonal elements A. As you see, A22, A11 are interchanged, A12 and A21 signs are changed. For 2 by 2 matrix, it is easy to find the inverse. How is the inverse calculated for 3 by 3? Computing the adjoint of A n by n gets tedious as n increases. So, we use Gauss-Jordan technique by employing row operations to obtain the inverse of the matrix A. Recall, if Ax is equal to B, to solve for x we do the augmented matrix AB and carry out row operations till we get RREF of A. We do the same now. Remember, when we do A into A inverse is I, we essentially need to find the elements of A inverse. Consider the following matrix: A is equal to 1 2 3 3 1 2 2 3 1. Let B the inverse of A. So, B, if you write down B11, B12, B13, B21, B22, B23, B31, B32, B33, we therefore have, when multiply A and B we get I. So, multiply 1 2 3 3 1 2 2 3 1 A and B matrix B11, B12, B13, B21, B22, B23, B31, B32, B33. If you multiply these two products, we should get identity matrix 1 0 0 0 1 0 0 0 1. This essentially is the same as solving 3 sets of simultaneous equations, namely namely 1 2 3 3 1 2 2 3 1 B11 B21 B31, that is 1 0 0. Similarly, we multiply the matrix with B12 B22 B32, that is the second column, that is equal to 0 1 0, and again the matrix multiplied with the third column B13 B23 B33, that is equated to 0 0 1. Therefore, we can augment A with I and do RREF. As we get RREF of A, we get the inverse of A. The augmented matrix is given by 1 2 3 1 0 0 3 1 2 0 1 0 2 3 1 0 0 1. So, R2 tends to R2 minus 3 R1, R3 tends to R2 minus 2 R1. These two steps will clear first column of A below the first row pivot entry. As you see, 2 zeros in the first column of A. So, the result is 1 2 3 1 0 0 0 minus 5 minus 7 minus 3 1 0 0 minus 1 minus 5 minus 2 0 1. R3 tends to R3 minus R2 divided by 5. So, we get 1 2 3 1 0 0 0 minus 5 minus 7 minus 3 1 0. then last row 0 0 minus 18 by 5 minus 7 by 5 minus 1 by 5 and 1. R3 tends to R3 divided by minus 18 by 5 in order to get 1. So, it will be 1 2 3 1 0 0. Next row 0 minus 5 minus 7 minus 3 1 0. Last row 0 0 1 7 by 18 1 by 18 minus 5 by 18. R2 tends to R2 plus 7 R3. R3 is multiplied by 7 and added to R2. So, it tends 1 2 3 1 0 0 0 minus 5 0 minus 5 by 18 25 by 18 minus 35 by 18. The last row 0 0 1 7 by 18 1 by 18 minus 5 by 18. R1 tends to R1 minus 3 R3, then 1 2 0 minus 3 by 18 minus 3 by 18 15 by 18. Second row 0 minus 5 0 minus 5 by 18 25 by 18 minus 35 by 18. The last row 0 0 1 7 by 18 1 by 18 minus 5 by 18. Now, R1 tends to R1 plus 2 by 5 of R2 in order to make 1 in the second row. So, that becomes 1 0 0 minus 5 by 18 7 by 18 1 by 18 second row minus 0 minus 5 0 minus 5 by 18 25 by 18 minus 35 by 18. Last row 0 0 1 7 by 18 1 by 18 minus 5 by 18. R2 tends to R2 by minus 5. So, when you do that, you see that left hand side you get identity matrix 1 0 0 minus 5 by 18 7 by 18 1 by 18 1 by 18 minus 5 by 18 plus 7 by 18 7 by 18 1 by 18 minus 5 by 18. The first as you see that the first one is identity matrix, second has to be A inverse. Let us check if A inverse into A is I. So, minus 5 by 18 into 7 by 18 1 by 18 1 2 3, that is original matrix 1 2 3. 1 by 18 minus 5 by 18 7 by 18 3 1 2 7 by 18 1 by 18 minus 5 by 18 2 3 1. So, when you multiply these two, you see 18 by 18, that is 1 0 0 0 again 18 by 18, that is 1 0 0 0 18 by 18 again 1, that is equal to identity matrix. Thus, we see we can use iterative techniques to obtain the inverse of a matrix by the Gauss-Jordan technique. To summarize, in this lecture we looked at the determinant of square matrix, its properties, and looked at defining inverse of a square matrix, properties, and how to obtain inverse of a matrix iteratively. In the next lecture, Professor Arul Alan will talk about importance of inverse. We will then take up Cramer's rule for solving Ax is equal to b. Namaste.